Hello folks, how's everybody doing? Hope you're doing fine. Today I'm going to be reviewing a little bit of what I covered in JFG's program, black holes. They're so popular lately, for the last 2 years at least I would say, since they LIGO smashed two of them and caught a hold of gravity waves, and then the other day they took a picture. Picture of a black hole. Now, how's that? That was how much time did you think it was going to take before they really had a picture? Unfortunately, there's a lot of material to cover, and sometimes 1 hour is not enough because you got to cover this angle, this stuff, this stuff, this stuff. You got to go through the whole thing in order to understand the whole picture, to see the whole picture. And 1 hour is usually not enough. So all I can do is kind of rush through it today, and hopefully you'll get at least most of it, most of the big picture. And that's my only hope today. Okay, so let's get going. Before we get going, I've got to remind you that we have on the 8th of June, we're going to have a conference, the Rational Physics Conference in Bora, Sweden, and that's a little over a month. We're a month away from this, and so make whatever reservations you need if you plan to go. Okay, notify me through the Patreon site. Just leave a message there if you're going, or you can find me on Facebook and just leave a message. Okay, let us know if you're coming. Okay, so let's get on with it. How did I start the discussion the other day? Well, I started with saying that there's a difference between mathematics and physics, and that I claim that mathematics is not the language of physics. It is not the language of science. It has nothing to do with science or with physics. And of course that upsets a lot of people because this is what everybody's been born to believe in. It's more or less like you're born in a Christian family, you're born with God, right? And this is the way people are educated or raised, or this is what they learn in school or wherever. And this is the worldly wisdom. How can you say that mathematics is not the language of physics or of science? And it comes down to a definition. First, you have to define what science is, what physics is, and if there is a provision for mathematics, well, then mathematics is. It's welcome in there. If there is no provision for it, then we got to get rid of math regardless of what tradition tells us or what they've told us in school. And I define science as rational explanations. Physics involves rational explanations of mechanisms involving objects. You need to have objects to do physics. You can't do physics without objects. And if those are the definitions, if we go with those definitions, there is no provision for mathematics. Mathematics can only describe, has no power whatsoever to explain. That's why math is not the language of physics, of science, and has nothing to do with physics or science. We do not use equations, we do not use variables, we do not do calculations or solve problems, not in science. Because science is what? Rational explanations. Mathematics has no power to explain, only to describe. And I synthesized that in a little picture here that you can see. And you can see that mathematics, you go to the show, you see the magician cut the lady in half. The mathematician can only describe what he saw. He can say, look, you have x equals AB plus C, where A is equal to head, B is equal to torso, C is equal to legs. The guy took 20 strokes of the saw, 10 seconds, and cut it in two pieces. He can describe what he saw. He cannot explain, which is what we see on the right-hand side there in red. That's what physics does. It tells you what the mechanism of the trick was. In one case, one theory says, well, the lady was under the stage. Okay. Now another one says there's two ladies. Okay. And the third one says, well, there were two ladies, but they were positioned differently. Those are the kinds of things that physicists must do. Physicists must be able to explain a mechanism. Okay. And here's a definition so that we know what we're talking about. We have description versus explanation. Math describes, physics, science explains. A description is just a listing of properties of a physical object. Okay? We use adjectives to describe objects, and we use adverbs to qualify or characterize motion. So you describe a chair, it's brown, has four legs, a backrest, a seat. That's a description. You can say it's mathematical. Yeah, great, it's mathematical, but you haven't explained anything. And that's what mathematics does. Mathematics has no power to explain. Physics, on the other hand, says, look, we want to know what the causes are, what caused something to happen. It's a physical interpretation. And the way you do this is you make a movie of the mechanism so that a person can watch the movie where you have images, where you have objects. And when you do that, the person can understand what you have going through your mind just by watching the movie. Essentially, that's what an explanation is. Okay. So I gave an example, and the example goes something like this. You see this in the night sky. You see, in the dark. You can't see what the cowboy is doing, but you see that the donkey is moving towards him somehow by magic so far. You just see this in the distance. Maybe your eyesight's not good. Maybe there's too much darkness. Who knows? But you can't see the mediator. Okay? So what are you going to put in there? Are you going to do this with particles? Are you going to do this with waves? What are you going to put between the cowboy and the donkey to explain pull to someone? Or what is it that you imagine off the top of your head when you see this image? You say, oh, I know what's going on here. It's going like this. Are you thinking of throwing particles? Are you thinking of that the cowboy's throwing waves? And here's with particles. I mean, is this what he's doing? He's throwing particles at the donkey. Is that how he's attracting them? Is this how you would simulate? Is this the movie you would make for me to explain this phenomenon? How about waves? Okay, here's waves. Is this what you do? Throw waves at the donkey? Is this how you attract the donkey? And yes, you do have to put a mediator, a physical mediator. Otherwise, you won't be able to explain this phenomenon that you're seeing. This thing that's happening. Okay. You need to, if you're going to explain a mechanism, it's going to have to be with physical mediators. You can put angels in there, but it's up to you, if that's what you believe in, if that's how you're going to explain your theory. But even angels, what is the guy throwing angels at the donkey? And how would that attract the donkey towards the cowboy? Now, what we all do mentally, and the way we would explain this is very simply, we do it with this rope. Okay? What we do is we say, look, the cowboy simply tied a rope around the donkey's neck, and he's just pulling on it. That's how we explain this phenomenon. Very simple. In fact, the only way you can explain the force of pull in real life out there in space with elongated objects. You need an object, it's got to be elongated. And you have all these people out there, they say, oh, I have a new theory. And the new theory is always an old theory. The old theory is always particles or waves. That's it. That's all they ever thought in the last 400 years. Some people say ether. What's ether? Particles, usually. Waves, what's waving? Particles. So we're back to particles. So ether is a particle theory. In fact, the issue is, you got to tell me what your atom looks like. And if your atom is this electron bead that goes around the proton ball, you got a particle theory. I don't care if you call yourself the electric universe or some of these other guys that go out there and try to explain their theory. You need a picture of your atom. That's the starting point. You need to have an atom. And if you can't explain how the electron remains faithful to the proton, you don't have a theory. You can't even start your theory because you're starting with a base that's already unimaginable. It's irrational. Okay. So the thing that you got to do is draw an atom. That's important. Okay. So anyways, the only way you can explain pull in the universe out there is with elongated objects. And people don't like that because people say, well, I'm going to do it with concepts. They're going to do it with fields. They're going to do it with energy. They're going to do it with mass bending space-time. All that's garbage. All that's nonsense. You can't do it with those because those are all concepts. Concepts don't bend concepts. And they said, well, I can understand it. No, you don't. You understand it when you can make the movie. That's when you showed me that you understand. Otherwise, you're just giving verbiage. And that's it. That's all I can tell you. Okay, so how would you explain breathing? Here's a good one. Here you have this guy, and he's huffing and puffing. And how are you going to simulate this? You're going to simulate it by putting particles in there. Here's a starting point. You see the guy breathing. You want to explain this to an extraterrestrial or to your little boy, right? And you say, what are you going to put as a placeholder for oxygen? Well, you're going to fill the place with particles and say, look, there's a bunch of particles. We'll call them molecules, atoms, whatever you want to call them. I don't care, X's. And those are penetrating my nose. We don't see them, but that's how you would simulate this phenomenon, breathing, simple phenomenon. It's an invisible phenomenon, and the way you do it is by putting a placeholder. And the placeholder is going to be particles, some kind of thing that's out there and penetrating your nose that you can't see. So you do it with objects. You don't do it with concept. You can't say, oh, fields are entering my nose, or energy is entering my nose, or mass is entering or force, or whatever. No, what you say is you put a particle there. Then the person can understand what you're talking about. And so this is important to go in there and make a visual, an image of what you have in mind. Make a movie, make a film, okay? That's the way it works in science. Essentially, a physical theory is one that you can put on the screen, on the big screen. That's a physical theory. That's a physical interpretation. And that's essentially what we don't have today because we have mathematics. We have equations, and they tell you, well, all we have is analogies, and we cannot really put this into words because words do not represent exactly what we learn in college with the math. You really got to take the math in college if you want to understand. But see, the problem, you're not understanding. What you're doing is describing, not explaining a mechanism. And of course, that's why the mathematicians rejected physical interpretations as being philosophy, metaphysics. No, we do real physics, we do equations. It's the other way around. What we need to explain is how a magnet works. We need to explain how gravity works. And for that, in order to accomplish that, you have to make a movie. You have to put pictures. It's all kindergarten stuff. You don't have to go to college. In fact, Mother Nature never went to college. I'm sure she would not understand all those X's and Y's. She says, look, just tell me how I'm doing my magic trick and show me the trick, how I do it. And she must be using some kind of invisible object there that we can't see, but it's an invisible object, and that's how she does her magic. That's how you would have to explain it. And we don't have that today. And that's why we have a lot of nonsense today about black holes and all this stuff, which is the subject of today, by the way. Okay, so here's another little bit. This experiment that I'm going to show next, it cost me $1 billion. So, it's a very expensive experiment. I would appreciate you sending the checks in the name of Bill Gates. Here it is, okay? Take a domino, and it falls. And you say, well, how did I do that? Did I do that by magic? And, you can break your head, think of whatever you want. And you say, Bill, what you did is you tailored that movie. I'm looking at a fake movie. And yes, you are. I did fool around a little bit with it. Here's the real one, okay? Now you know how it fell? See, that's how it fell. But see, if I make all these things invisible, you say, how did it fall? Did I do it by magic? Well, I'm sure Mother Nature doesn't use magic to bring down dominoes, okay? No, the way you do it, you go in there and you do it with a row of dominoes. And if the dominoes are invisible, you make them visible for the person to understand the mechanism. That's the way we understand mechanisms. Once you see this, you say, oh, that's kindergarten stuff. But here, this is magic. If you saw this suddenly in front of your eyes, someone doing something like that, you say, how did he do that? Did he blow it down with his air? But even in that case, you know that there's a physical object. How did we do breathing a minute ago? We put particles, right? So you have to say, if you're going to simulate this for someone, if you're going to make the physical interpretation of this movie, you would put some kind of object in there. You say, look, that did not fall all by itself. Something pushed it down, okay? And that's the point. The point is that physics requires physical interpretations, and you can only do physical interpretations with objects. Okay, can't do it without objects. Okay, so what's the issue? Well, the issue is that we have this little thingy that they call black hole. Very mysterious kind of thing. And you say, well, why is it mysterious? Well, I'll tell you why it's mysterious. Mysterious because we don't have a definition. That's the starting point. Here we have two definitions. We have NASA and we have, the Max Planck Institute, okay? And what do you see? Well, you see a definition, not really a definition, but it tells you what a black hole is according to NASA. It says a great amount of matter packed into a small area. And all the words that you see underlined, small, sphere, diameter of New York City, tiny, big, those refer to something that has volume. It has diameter. It has radius. You're talking about something that is greater in volume, in size, greater than zero. That's not what the Max Planck Institute says on the right-hand side there. It says, a black hole is not a tangible object, but a region in space. So is a black hole a region or is it a ball? Well, the other day, JFG, I think he's completely mistaken on that issue, and we didn't pursue it, because obviously we can't spend the time just arguing over a point. But here I'd like to clarify that a little bit, if I may. Here I have a difference between a region and a ball, okay? Okay, you have a fish tank, water tank there, okay? And let's say you were able to somehow isolate a region, a spherical region, perfectly spherical region within the fish tank, okay? That's a region. Is that the same thing as a standalone ball? Well, if you pull that region out and, like in a balloon and bring it to me, you say, look, this is a ball. Yeah, that is a ball. What you're showing me, a balloon full of water, yeah, you can argue that that's a ball. But that's not what a region is. The word region represents a concept. Region is always of something else. In this case, we're talking about a region of the fish tank, okay? Or the water, volume of water. So we're talking about something of something else. Objects are standalone. They're not dependent on anything else. If you're going to talk about the halo of an angel, you need an angel. Otherwise, you got a ring or a plate. If you want to talk about halo, like holy, angel, that kind of thing, you're going to have to put the angel and say, look, he's part of the angel. That's why the ring or the plate or whatever he's got in his head, it's holy. Why is it holy? Well, because it belongs to the angel. Without the angel, all you have is a plate or a ring. That's a standalone object that's objectively in front of you. And likewise with this, you don't have a ball. A region is not a ball. And that's why it's important in physics. Physics can't be done without objects. Next step, you need to define what an object is. You absolutely need the word object in physics. This is not ontology. This is not metaphysics. This is laying the foundations of physics. You need to tell me what an object is. No one has done so in the last 10,000 years. Not a single book of physics, textbook of physics, begins by defining what an object is. And the word object is very important. And people want to redefine the word object. It doesn't work that way. See, when you look at the rope model, all these words are already defined. what an object is, what location is, motion, exist, distance, dimension. And you can't fool around with those definitions because one definition affects the other. They're all tied together. If you move one, you're going to move the others. You're going to change the whole thing. So you have only two options. You can criticize the definition, say, I got a better one, okay, let's hear your definition. But you can't just pull one definition out of nowhere and say, look, this is my definition of object, this is my definition of exist, or whatever. You got to put them all together. You need them all together because you're going to use all of them. You're going to need to know what a location is. You're going to need to know what motion is. So you can't say, well, I'm just going to define object. And I like the word touch for object. Anything you can touch is an object, for example. You can't just do that. You can't just pull it out of context and say, I'm just going to define this. You got to define it all because you have to lay the entire foundations of your physics. Okay? And then you got to compare them against what I wrote down. So we have something to compare. Yours against mine. You just don't compare one word. You compare all of them. You need a body of words to do physics. Okay. Okay. So what's the problem with this ball versus whole or 2D plate or region of space or space-time? Well, here's the problem. The problem is that what these people have done is they put a hole and they tell you that's the one on the left there. It's a hole, and they say, look, that's a black hole. But see, in other contexts, they say, well, it's really a ball. It's the one on the right. So we have a hole which goes through space-time, through this wormhole. But the important thing about a hole is that it can only be on the surface of something. Like in this case, the hole is on the surface of space or space-time, whatever that black cube means to you. Okay, so it's on the surface of space or of space-time. You can't see a hole inside the body of an ocean or of the ground. No, you need to see a cross section, and you should be staring at the surface. Like if you see Bugs Bunny's hole from the sky, that's how you would see it. You have to see the surface of something to see a hole. On the other hand, the ball, you can see it inside the cosmic ocean there. You can have the ball in there, no problem at all. So these are two different notions of what a black hole is. And there's also the problem with gravity. See, in the case of the hole, supposedly it goes into the hole through a wormhole into another universe. In the case of the ball, the gravity goes towards the center of the ball. So we have two different notions here. We have, on the one hand, gravity going through the wormhole, and the other one, the gravity going to the center of a ball, to the singularity. So which is it? See, we can't have it both ways and win. A black hole is one or the other. And we have another image from NASA, which shows you that this is exactly how they paint it. And they say, well, don't take it literally because it's just an analogy. And here they show that you have this hole. That's the entrance to a wormhole, which is very thick there in this case. And they put this as science, like this is in the NASA site. It's not in a cartoon site. This is not Bugs Bunny and Friends. This is not Merry Melodies. This is a science site, and this is what they illustrate. And of course, when you criticize this, they say, oh, but you're criticizing the analogy. And so it's like you never win because they don't have a physical interpretation for this. That's the issue. The issue is if they're going to do math, we don't care. They can do math all they want. But they can't say, look, I'm going to give you a physical interpretation. It's not going to be literal. It's going to be an analogy. Okay? That's like taking the Bible and saying, look, I'm not going to read it literally. I'm going to interpret it for you. See what I'm saying here? When you say, well, did Jesus walk on water? And you say, well, it was really ice. Oh, yeah, I can walk on ice too, then it's no miracle. Did he go to heaven? Or, did he spill his blood for me? Well, yeah, but see, the blood is really the wine. And, and they go through all these analogies. Well, did he die on the cross or not? I mean, just be straightforward about it. Did Moses part the seas? Did Jonas get swallowed by a big fish? I mean, are these real? Are these real scenarios? Or are we just going to interpret them and say, well, he wasn't really, Jonas was not really swallowed by a fish. That's an analogy for all the suffering that Jonas had. I mean, they can interpret anything they want. And this is the same thing. Here, these people give you an analogy. They say, well, we have this wormhole going through space. How did you get that? Well, I got it from an equation. It's called the Einstein-Rosen bridge. Okay? Here's the equation. Fine. Okay? There's the equation. What does it represent? It represents a wormhole going to another universe. That's what we interpret from this equation. So this is your physical interpretation is a wormhole. Yeah, but it's an analogy. An analogy of what? Either the equation represents that 1D string going from one universe to another, or not. It's a black and white issue. I mean, an analogy has to serve for some purpose. It's got to be of something. A simile, a metaphor. It's got to be of something. In the end, you have to produce the real thing. And these people don't have a physical interpretation. When you attack their analogy, they say, you're raising a straw man. So why did you enter into physics to begin with? You're trying to tell me that your equation has more than I think, to do with physics, because you can interpret the physical world with your equation. That's what they're saying. So they're the ones who's taking the step into physics, called mathematical physics, right? So they're taking the step into physics, and now they're saying, we're going to interpret the universe for you. We're going to tell you how this universe works. There are black holes, there are dark matter, there was Big Bang, there are particles coming from the future, tachyons and so on. They'll interpret the whole universe for you. And you say, well, it's so fantastic. I mean, do particles really come in from the void? You're attacking a straw man. See, that's just a figure of speech. You really got to take math to understand it. So we end up not understanding anything. For them to say, look, you got to take a course in math at the university to understand what I'm talking about, well, then all they have is a description. They don't have a physical interpretation. Why did they try to give a physical interpretation to begin with? Why did they venture into physics and say that math is the language of physics if they cannot give you physical interpretations, and whatever they give you is an analogy, and if you attack the analogy, they say you're raising straw men. So it's circular reasoning, okay? It doesn't work. Okay, and here, let's just put the final touch on that. Here's a fella who wrote this, and I liked it, so I thought I'd bring it in. He says he ran against, this is a guy who believes, by the way, in relativity, okay? So I'm not bringing someone who's against them. It's quite the contrary. This guy's a relativist. But he says, space-time is not a fabric. Space-time is not a rubber sheet. Space-time does not bend, stretch, ripple, or tie-dye. So why do people tell you that it does those things? They don't want to try to teach you the messy, tricky, complicated. You really need the math to work with this stuff. They give you an analogy, but analogies are also dangerous because they are inherently wrong. You don't really understand. You just have the illusion of understanding. And if you are the sort who really does want to understand, then you are going to push the analogy and try to use it to understand more deeply. And the lie implicit in the poor analogy will rise up and bite you. Space-time is the set of connections between things, events. By the way, the word connections here, that's not physical connection. Those are abstract mathematical connections. In other words, those are abstractions, not real physical connections. So the word connection is a little misleading there. And he ends, he says, so space-time isn't really a sort of thing that can rip. It isn't really a sort of thing at all. And at the bottom, we have a little cartoon, somewhat popular, where you have a professor explaining gravity with an analogy, saying, oh, it's the bending of the rubber sheet. The student says, oh, so it really, we have this thing weighing down. Is that what causes gravity? And professor saying, "Oh my God, no, look, you really, this is just an analogy. You don't have to pay attention to the analogy. If you really want to understand this, space-time is, like the set of equations, okay, for which the analogy is only an approximation." And the student says, "Oh, that's so boring." And again, it is boring. Why is it boring? Because people want an explanation. People want a mechanism. And these people are saying mass warp space. Okay? Mass warp space. Bend space, there's a depression. The bowling ball falls to the center. Okay, we all understand that. We see that. We have that experience here on Earth. So you can do it on your couch. Put a bowling ball in the center, put a little golf ball. You'll see how it'll twirl around and then fall towards the center. At least that part you'll be able to simulate. But then they say, no, that's an analogy. That's not the real thing. You really want to understand it? Go to the college, take calculus, linear equations, whatever, and then you'll understand. No way, because the equation supposedly is a description of the real world. And if they don't have a physical interpretation for that, then the equation is not representative of the real world in the sense of telling you what is doing things out there. It doesn't identify the invisible mediators out there. That's what an equation cannot do. No mathematician can do that. They cannot tell you what light is, what gravity is, what electricity is. And they say, well, electricity, we know what electricity is, a flow of electron beads from atom to atom. Well, is it? Well, for this, you need the planetary model of the atom. Is that correct? And they'll tell you, no, that's not the real atom. And how about the particles? Well, those are not really particles. They're excited fields. And so on and so forth. You're always dealing with concepts. You never get to the real meat. You never get to see the mediators. And the real reason for that, the reason behind that is they never figured it out in 400 years. They're still dealing with particles and waves. And that's the real problem. They're still dealing with particles and waves. Okay, and just in case you say, well, is it possible to make wormholes? If you have a hole, like in the case of the hole of the black hole, we have the ball and we have the hole, right? You have the hole, and it goes through a wormhole into another universe. In other words, they say that the hole is essentially a puncturing of space-time. A lot of people deny this, but that's what they're showing. What is an Einstein-Rosen bridge? What is a wormhole? A wormhole is a little one-dimensional, string, spaghetti, something going through space. It's a hole in space that goes from here to there. That's the notion that they have. And they might say, well, that's an analogy. And they keep going with this analogy deal. But that's what they're illustrating. We want a physical interpretation. And if these people are saying that we can go to another universe through a wormhole, the analogy is for real. They can't say, well, if you attack that, you're just attacking the analogy. No, because you're telling me that your theory is that I can go through to another universe through a wormhole. So if that's what you have in your mind, if that's your theory, if that's your proposal, don't tell me it's an analogy, because your analogy is the real thing. Otherwise, you got to say that that's bunk. You can't have it both ways. You can't say, I can go through another universe through a wormhole, but don't attack the wormhole because that's just an analogy. Yeah, but it's the foundation of your theory, and your theory is that I can go to another universe through a wormhole. So you can't keep going in circles. You can't say this is true, but don't attack the analogy. You see the problem? And just in case, we have why we need, to convert space into something, into a physical object. More than a physical object, a very solid, rigid, physical object. And here you have it. Mr. David Blair, he's a PhD, so if you want authority, you won't have more authority than you'll have with this Australian. And he's got a lot of gold medals that he won at the Olympics, okay? You can see there he's got all kinds of awards. He says space is a very tangible material with tangible properties like stiffness and shape. The most important thing to keep in mind about Einstein's universe is that fantastic stiffness of space, of the rubber sheet, if you like. The stiffness of solid steel is about 10 to the 11. Space has a magnitude of about 10 to the 43rd. Space is a billion times stiffer than steel. PhD in physics. This is what he learned after 10 years at the university. Huh? What do you think? Am I raising a straw man? These people are saying that space is a physical object. They had to turn it into a physical object. Then they built an Einstein-Rosen bridge, a little one-dimensional line that goes from here to there. The entrance is a zero-dimensional black hole. When you attack all that, they say, oh, but you're attacking the analogy. You know, we have no way of presenting our quantitative analysis in qualitative language like English, for example. We can't put it in words because words do not really match up with our equations. But if that's the case, then math is not the language of physics, because they can't tell me how a magnet attracts another. They can't tell me why a pen falls to the center of the earth when I let it go of it. And so on, they can describe and say, look, the pen fell at 9.8 meters per second squared. That's the acceleration of gravity. Yeah, that's a description. What's the mechanism? And they say, well, that's philosophy. Then your equations cannot tell me. Your equation cannot tell me what the mechanism is. So why did they try to give a physical interpretation in the first place? If they claim that their math, their equations, their variables are not representative, right? Then they cannot simulate the mechanism with their equations. They can only describe. Then math is not the language of physics, because if physics is telling me what the mechanism is, then math is not the language of physics. And it's hard for people to understand that today. They say, oh no, we've gone 400 years with math and physics. You're going to take it out now? Yeah, exactly. I'm going to take it out now. We don't need math and physics because all it does is get in the way. Right now, people say, where's the math? Where's the equation? Who was the authority who approved your paper? We don't need any of that. We need to figure out what the mechanism is, and we're done with physics. We need to figure out what invisible entities Mother Nature uses to run her shop. That's what we need to figure out. We don't have that today. We don't have it anywhere. And so this is what's on the table right now. These are the issues, okay? Okay, wormholes. Am I raising a straw man? Here's a documentary. Documentary, okay? This is Mr. Brian Greene going through a wormhole, okay? He talks to himself in the morning, shakes hands with himself hours ago. He just jumps in the wormhole and travels. Now, is this a sci-fi movie? Is this a cartoon? Is this a joke? Am I supposed to take this seriously? No, this was put on supposedly on a documentary. And this was one of the things. They show him going to a black hole. They show him with this block of time. They show so much nonsense, and they call that science today. So something is wrong. Something is definitely wrong if you're going to say, oh, that's science. Oh, it's breathtaking science. I mean, is that science? You jump into a wormhole? I thought a wormhole was zero-dimensional. Why did he put that in there? To impress you through, he made a movie of his theory, right? Which is what I'm requesting. Please make a movie of your theory. There he made a movie of, he put a wormhole. Is the wormhole zero-dimensional, has a zero-dimensional entrance? No, it's got one big enough for him to jump in. That's the first problem. Was the wormhole one-dimensional? No, it was a tunnel. At least two-dimensional, I would say. Three-dimensional if you include the length, right? To the other universe. And did he go to another universe? No, he traveled through time to the morning where he saw himself. This is science. I mean, think about it. Folks, if you have your feet on the ground, this is nonsense. This is not a documentary. This is cartoon. This is whatever it is. I don't know. Certainly it's not science. Okay, here we have more nonsense from the black hole. Here we have Mr. Stephen Hawking. I'm not going to read all of it. I'm just going to say that this comes out of his book, Brief History of Time, where he mentions Chandrasekhar, who won the Nobel Prize for saying that a black hole collapses to zero-dimensional. So I'm not raising straw men here. Chandrasekhar won the Nobel essentially for his work on black holes, and his primary idea was that a star can collapse to a zero-dimensional singularity, a mathematical singularity. So, again, this is not nonsense that I'm bringing up. This is an equation that says these are conclusions. An object, a star, has so much mass that it compresses all the way until all structure ceases to exist. It disintegrates, and all we're left with is a zero volume, zero radius, zero dimensional singularity. What is a singularity? A mathematical nonsense. And that mathematical nonsense supposedly has an effect on a real star far away that we can see. So you got to ask yourself, is this a science? Is it science? Just because it comes from PhDs like Blair, who says that space is stiffer than steel? Is this what we're supposed to believe? I mean, you might not, how can it possibly be? We've got GPS, we have computers, quantum and relativity have to be correct. And again, technology has nothing to do with it. And people have a hard time understanding that, but Iran, the Iranian mathematicians, they know about as much as mathematics as anyone in the West, or more. And they know also, all the equations. They know all of relativity. They know all of quantum. They don't have a bomb. They have mathematics. They don't have technology. So don't tell me that technology is proof of, that a theory is correct, or vice versa, that mathematics generates, technology. It doesn't work that way. The way technology works, we develop it by trial and error. Mr. Thomas Alva Edison said it perfectly. He says, I have not failed. I found 10,000 ways that don't work. He tried one thing right after another until he got it right. Edison died without knowing what electricity is. He didn't need to know what electricity is. He didn't need to have an equation on his hands. All he needed to do is try something in the shop until it worked. And you can do this with magnets. You can try a magnet every day and pick up pins. You don't need to know what a field is. You don't need to know how fast you're pulling it. You don't need to have any Gauss or force or anything, any mathematical quantity. All you need to know is, does the magnet pick up a piece of metal? Yes, it does. Does it pick up this one faster than that one? That kind of thing. And you can do that, by trial and error. So technology is developed by trial and error. It's not proof of a theory. Certainly, GPS does not prove that time is a physical object, which is what relativity says. It treats it as. And certainly a computer, the fact that it works, does not prove that a particle can be at two places at once in quantum decoherence. So it's nonsense to say that technology proves the theory, okay? So don't tell me that, we wouldn't have computers if it weren't for quantum. That's an argument of idiots, people who are not familiar with the scientific method, okay? So just keep that in mind. Computers do not prove quantum. It proves that the person who makes that analogy or that argument is not familiar with the scientific method. That's what it proves. Anyways, Hawking radiation, here's another little bit of magic. Hawking invented this nonsense to give astronomers something to do. He says you have two particles, And as we all know from quantum, because quantum is right, never wrong, right? A particle can come out of the vacuum and it splits immediately in two. Okay, one becomes the positive, the other one the negative, whatever positive and negative means in physics, and they split up. One falls to the singularity. Why does the other one leave? Why would it fly away if gravity continues beyond the event horizon? I mean, if gravity pulls on that sun, on that star that's over there on the upper left-hand corner, that distant star there, if gravity can pull on that and force it to go around the black hole, why would the little particle that just split from its twin, why would that one fly away to your eyes? That's what they have to explain. They can't just tell me one falls into the black hole, to the singularity, the other one flies out, and that's why we can see light coming out of a black hole, because we have all this X-ray or material that we can measure and see. If that's the case, why doesn't that light also fall into the black hole? And they say, well, it travels faster than light. Who cares if it travels faster than light if gravity's pulling on it anyways? Why would it go to your eyes? Why does it fall in as well? And again, they have to make it travel faster than light. And they say, well, it's outside the event horizon. Therefore, the velocity of light stops there. Okay? But see, that doesn't mean that the particle is going to go flying to your eyes. Why doesn't the particle fall? I mean, doesn't gravity bend light? Okay, so it should bend that piece of light also around the black hole. It doesn't bend it as quickly as, in a closed curve like the one on the inside. But it's still, that particle has no chance of leaving. Why would it reach your eyes? See, they make this magic like one is affected by gravity and the other one is not. That's the problem. And then they tell you, on the other hand, again, because they have all these contradictions, they say gravity does bend light. Well, if it bends light, we could have bent that one as well. I mean, it should send it in a different direction as a minimum, right? So you figure it out. Okay, so does a black hole do this? This is even bigger magic. Here you have mass bending time. Now, how's that for a magic trick? Okay, mass bending time. What is it? The fishnet. Does that make any sense to you? Because this is what relativity says. Essentially, it says that mass bends space-time. Time is a function or a part of space-time. So if mass bends time, what are they talking about? We have a concept bending another concept. Does love bend intelligence, or what is this? So this is nonsense. This is absolute nonsense. And again, if they say, well, this is just an analogy, you say, well, then your math does not describe the real world. In other words, put it in physical terms. What does mass bend space-time really mean? And they can't put a bowling ball on a canvas and say, this is what it means. Okay, then I'm going to criticize that because that's your interpretation. You can't accuse me of raising straw men and saying, well, but that's only an analogy. Analogy of what? I mean, you're telling me that the reason the Earth, which is a real object, right, goes around the sun is because the sun weighs down space-time, right? That's your interpretation. That's what you're telling me that your equations tell you. And so your theory is that, yes, the sun does weigh a physical canvas called space-time, and that compels the Earth to go around. Because that's what the field equations of general relativity tell you. So don't tell me I'm attacking a straw man, because that is your analogy is the real thing. I gotta explain how the Earth goes around the sun. You can't tell me, oh, that's an analogy. You're attacking a straw man. No, of course not, because that is your interpretation. You're saying that your equations tell you that there is a canvas. The sun weighs down this physical canvas, and as a result of weighing down the physical canvas, the physical Earth goes around the sun. That's what the theory is. So there is no analogy. It's the real McCoy. And so keep the argument in mind, because these people want to, when they explain it to you, they give you their so-called analogy, but that's the real thing. And then when you attack their analogy, they say, oh, but you're raising a straw man. You got to do it. You got to attack my math. No, I'm not going to attack your math. I'm going to attack your physical interpretation of your math. Because if you tell me that your equation tells you this, but then you're going to dismiss and say, well, that's just an analogy, then your equation does not explain how this universe works. It's your physical interpretation of your equation that I'm attacking. And your equation can't help you at all there because he's interpreting his equation, okay, for you. Okay. Nevertheless, we have the circular argument. If a black hole actually crunches matter out of existence, like you see there in the center, it crushed matter out of existence. We have two professors, one at University of Maryland, the other one at University of Toronto, saying this. I don't know how many more you need. You need Einstein himself to come in here and tell you this. If a black hole does singularity crunches data out of existence, like even Chandrasekhar said, then we have to accept it. That's what it says. You can't see the other day JFG denied that, that mathematics really says that. He said, well, some people take too much liberty with the language, and really, the black hole doesn't crunch matter out of existence. That's what Chandrasekhar proved. That's what he got his Nobel for, proving that singularity crunches everything out of existence, and there's zero-dimensional center of mass in the center of a black hole that creates this event horizon, this ball, this region of influence around it. And so, yeah, a black hole does crunch matter out of existence, but then mass is the quantity of matter. And if all matter is gone, then what do we have? We have the concept mass. We have no more elephant, but we have it's 6 tons behind. What does that mean? How can you have 6 tons without the elephant? And so, yeah, if it crunches or crushes matter out of existence, then I don't know what a black hole is. And that's why nobody can tell you. What are they going to say? That a black hole is just all mass and no structure? Is that what a black hole is? Is that what they took a picture of the other day? And yeah, they'll tell you, no, we took a picture of matter falling through the event horizon. Why would that light reach your eyes? Why doesn't it all fall inwards, none of it outwards? But see, they're saying some falls out, creates this X-ray when it passes the event horizon. The X-ray is what we are able to see, and that's what we took a picture of. It's like you take a picture of the spirit going into heaven. Okay? You got a little ghost, Casper the Friendly Ghost, Cheat. He goes to heaven, hopefully. He goes to heaven, and as soon as he passes the cloud, he sends an X-ray. Is that what this is? And they took a picture of these X-rays and compiled them and came up with this picture? Is that what they did? Is this how they do science? You gotta analyze what these people are saying. These people are saying some such weird, extraordinary stuff that you can't believe it anymore. Just in case, when all this is said and done, we have Mr. John Wheeler, and he puts us straight. He says, nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method, try to evaluate amount of matter, that number would not equal mass. We have no definition of the word mass to this day. Like I told JFG, the Wikipedia has seven different definitions or notions of what mass is. And as a mathematician, you can use the one you want, the one that favors your theory. So you can interpret this any way you want. You can take gravitational mass. You can take relativistic mass, inertial mass. You can take any mass you want. Quantity of matter mass. You just take any one that you need. So yeah, that allows for you to go in circles. It's like the word point. What is a point? Is it a dot that the guy drew on the board? Or is it the location? Or is it a number? Is it a set of coordinates? What is a point? Well, they don't know. They say we're not able to define it because it's a primitive term. And the black hole is in the same boat with its mass. Because if they can't define mass, what is a black hole if the black hole only has mass? So we got a problem here. We don't have definition. We don't know what they're talking about anymore. They don't know what they're talking about anymore. Okay? And let me close with this, which is what I showed the other day. For today, I'm going to continue with this subject next time because I haven't finished. But here I showed what the problem is. Here you have an elephant in depression because of its weight. And because of it created this depression, a turtle goes around and around this mass, this huge mass. We get rid of the elephant and just replace him with his mass. So we don't have an elephant anymore. Now we have 6 tons. And again, the mathematicians don't care what physical object you put in there. You can put an army tank if you want in there. They don't care because they say we have 6 tons and 6 tons produces this effect. Yeah, but 6 tons is not a physical object. You can say you have mass, yeah, but what is the object? You can't just say, I'm going to put mass, because mass is a mathematical concept. All you're saying, you're putting kilograms in there. You're putting tons. You're putting pounds, whatever. And you know, the question is, when we take a picture of a black hole, or when you ask the astronomer, hey, look through your scope, see what you see in that region, you're not asking him to look for kilograms, or for tons, or for pounds. You're looking for an object. And so since they couldn't find an object, they said, we know, you're trying to search for a singularity. No such thing. And the singularity has this region of influence, which is also not a thing, called an event horizon. So we have a singularity, which is not a non-object. We have an event horizon, which is a non-object. And these guys are supposed to look for it with their telescopes or with their X-ray detectors or whatever they use. This is nonsense. Okay, so what happens? The next step is we get rid of the background, okay? And, you know, here you can understand it because, more or less, because you still have the ground. But once you get rid of the ground, you're in completely an empty space. You have this turtle just going around, you know, mass. So how can that possibly be? You have a turtle going around mass. So what they do is they cheat, and of course they got to put something in there for you to visualize, because otherwise the general public is going to stop sending the money. So they said, look, you got this turtle going around nothing, right? Yeah, but see, really, the turtle goes around mass, and mass is weighing down space-time. This is the way they present it to you. You know, you have mass, okay? And what is mass doing? It's weighing down the fishnet. And we can all understand this because this is the movie they send us. In fact, the mass part, you would have to put the elephant in there. So we can understand this more or less. But now we get rid of the 2 concepts, first of the space-time and then of mass. And what do you have? You have a turtle just going around nothing. That's the physical interpretation. And they're saying, well, if you want to understand this, you really got to take a course in math at the university. And this is where we have a problem, because they're trying to get away with analogies on the one hand, which is their physical interpretation. And then when you attack the physical interpretation, the qualitative explanation mechanism, they say, oh, you're attacking a straw man. This is the problem we have today. And so with that, I'm going to see you next time. I wanted to present today the rope model. I was not able to do so because we ran out of time, but we'll go over it next time around before we resume the ether and the particles and the infinity of space. We're going to go back to that subject, but let's cover black hole so that we understand it well. We'll see you next time. Bye-bye.